Hi there. Now let's look at LeetCode 235. This is lowest common ancestor of a binary search tree. Given a binary search tree BST, find the lowest common ancestor node of two given nodes in the BST. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. Alright, so we are given a BST. We would like to return the LCA of P and Q. Okay, so I think the question is clear to me. We are given a BST and two different nodes. You would like to return the lowest common ancestor, meaning that the ancestor we need to find a node where it is positioned to be as low as possible, but at the same time P and Q are the descendant of the particular node. Okay, now let's look at the examples there. Examples, we have 6, 2, 8, 0, 4, 3, 5. From 8, we have 7 and 9. Now P is 2, Q is 8. P is 2, Q is 8. The lowest common ancestor is 6. Is that right? Yep. The LCA of nodes 2 and 8 is 6. Examples 2. We have the same tree, 6, 2, 0, 4, 3, 5, 8, 7, 9. So P is 2, Q is 4. The lowest common ancestor is 2. Okay. Third question. We have root 2, 1. So that would be 2 point to left 1, is it? Yep. Examples 3, we have 2, 1. P is 2, Q is 1. Answer is 2. Yep, it is correct. I think I got the questions. I would like to clarify a few questions. May I ask a few clarifying questions? So first one is, may I ask if there would be at least 2 nodes? And then the answer is the number of nodes in the tree is in the range of 2 to 10 to the power of 5. Okay. And unique, may I ask if they are unique, i.e. P equals Q. So it says that node.file are unique. Alright, and P is not equals to Q. P and Q in BST. Okay, so now that I have understand the questions, I would like to think about some possible approaches for these questions. Let's see. So I think one brute force approach that we can do is that we could go through every node, and then for each node we start from the root of the BST and then check if P and Q is in the subtree of the current node, and if so, we assume that it is the current LCA, but then we also check whether the children of the current node could be the LCA. So in this case, we move down to the child node and then check whether P and Q are in the child nodes, and so on and so forth until we got the lowest point where there is no longer a lower common ancestor. Then we return that particular node. So I think that would be a brute force approach, and that would be pretty slow, I think, because it would take for each node we are gonna explore all the children in it, right? So that would be like, I think, more or less O(n) squared, where n is like 10 to the power of 5, so it's pretty slow, I would say. Now I would like to think of some possible optimizations to this problem. Alright, so if we know that P and Q is in the subtree, then what if we move down to a tree and we see that it could be... Okay, let me just look at sample 1 there. So we have 6, 2, 8, and 2 and 8 happen to be the children of 6. So 6 would be the answer, and we don't need to further go down the tree. Right. But the second example there, we have 6, 2, 8, and both of the P and Q lies on the left subtree. So if we I'm thinking whether we could just traverse all the tree and then we back up. So when we back up, one point we will see that that P and Q is in the current subtree, then we return that particular node all the way back. So if I'm thinking of a recursive way to traverse the tree, and then if we at one point at a particular node we found that P and Q are the descendant of the node, then we just keep on returning that particular node, right? So as for the first example, we have 6, 2, 8. Then we traverse down all the way to the leaf node. So we have 0, 3, 5, 7, 9. And if we look at just one of them, like 3, 5, these both are not the value that we are looking for. So we back up. So we tell the parent that the P and Q cannot be found here. And then the parent said, P and Q, I am not one of them. So if the 4 will tell the parent, and the 0 will tell the parent as well that both of the children are not P and Q. And then suddenly 2 happens to be one of the P and Q. And then similarly on the right side, but then, okay, wait. So on the left subtree, we have one of P and Q, but it's not both. So that is not the answer, but it is part of the answer. Now, on the right subtree, we have 8, part of the answer as well. Once we return to the parent 6, at that point, we found that the child of the left child and right child have both P and Q, so we return 6. And then the second example, we have 2 and 4 on the left subtree. So 2 is the answers, and then we return it to the parent. We keep on returning until to the top it will return 2. And then the third example is the same. At the top it would be just 2. So we have found it out. Alright, does this sound reasonable to you? I have to think of how am I going to implement this solution if I'm going this part. Is there any problem that you see with my approach? I'm gonna assume the interview asked me to continue with the implementation, so I will ask, does this sound reasonable to you? Shall I proceed to coding? And then he said, yes. Alright, so we need to find a way to return a particular value and tell the parents that we have found the node that will represent the LCA. So how are we going to do that? Okay, let me think. I think we are gonna need something to count how many of P and Q have been found in the subtree that starts at the current node. Okay, so if we look at the examples 1, 0, 3, 5, 4, 7, 9 all have 0 count because none of P and Q is one of them. But at 2 will have count of 1 because it has one of P and Q. And then 8 also will represent 1. So we have count of 1. In the end, the root node 6 would have count of 2. Okay. So we kind of keep on going up step by step until we got to the point where the count is 2. So if we do it this way, we're gonna need a recursive function. So you recurse the left and right, and then we check if the left is true, left, right is true. This is an interesting problem. So if we recursively go through each of the nodes in the tree, and then we could get the sum of the count of the left, current, and right, then that would be quite efficient then. So what do we return at the end when we found it? So let's say we have a recursive function that returns the count, and then somehow at some point we found that the count is now 2, meaning that we have found the solution. But how are we going to decide that the current node is the LCA? Okay, so once we found the LCA, we need to stop the chat. Is it? Let's see. So if we have LCA, okay, how about this? If the current node is not an LCA, then we just return an empty null pointer, so as to indicate that it is not the solutions. But if it is, then we return the node, the like one of P or Q, whatever that is, and then we pass on to the top. So I think there are three cases that we can do. Case one is, so the base case we have A and B, or case two we have A, B, so P and Q. So let me just write P and Q. One case is P and Q are on one of them is a parent and then one of them is a child. Or another case is P and Q are children. So in that case, the parent is gonna be C. If one of P and Q is the parent, then they would be the highest one. That would be the highest one will be the answer. Okay. So now I think this sounds reasonable. Does it sound reasonable to you? Okay, I think we should go through some examples. So in the first example, we have 628047935. So let me just draw the tree for our convenience. Okay, so this would return none, 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 and none. And then this would return 2 and 8. Now this would be the answer. 6. Second example. We have 2 and 4. So we need to return 2. None, none, none. Then we return 2. Okay, well, I think we could just return the pair, but no, we cannot return the pair. So I think we need to return the count and also the pair. Hold on. If we just store it into a variable, so if we have like a P and Q is in there. So once we found the child node with both P and Q, what are we gonna do? We're gonna return it up. Okay, I think here's what we're gonna do. If P and Q are returned, if the children return both of the children return none, return a node, then you're gonna return the current node. However, if just one of them is returned, then we're gonna return that particular node. Okay, so we got that. I was a bit lost. So if the children is one of P and Q, then we return that particular node. If not, then it must be both of them are none, so we return none. So in this case, we return P. So let's say C and D, then we return none. Okay, does this sound reasonable to you? I'd like to start implementing unless you would like me to explore further optimization. Okay, let's do this. Now, what we're gonna do is we will check P and Q. Now let's say we have P. If the current node is P or Q, then we return the current node. So let's just write down the function first. Define LCA. Let's call it LCA. Root PQ. Okay, so if not root, return none. Can I return none here? Let's see. Okay, so I can return none. Okay, if not root, then return none. Otherwise, if root dot file equals p dot file, or root dot file equals q dot file, then we return root. then what we're gonna do next. So if P and Q are C, so we have 2 and 8. If we return it, okay, here's what we're gonna do. I think if we let's just call it left and right. So left equals LCA root dot left PQ. Okay, first of all, I need to check whether there is a left or right. So if root dot left else none, LCA root dot right PQ is root dot right else none, current equals root if root dot 1 equals P dot 1 or root dot 1 equals Q dot 1 else none. And then I'm gonna check if curl or left and right. Then I'm gonna return root. Okay. Else and if left, return left and right, return right. Else then I return none. Okay. Now let's go through our exam. Now let me go through the code again to make sure I don't miss anything. Here, first of all, I will check the root. If it is none, then I'm gonna return none, that meaning that there's no possibility that we find P and Q in the current node. Then I'm gonna check if the left subtree has any of P and Q, P or Q. And also the same thing for right. And also don't forget check the current root to see if it could be the solution. Now if curl or left and if the root is a part of the solution, then we return root. Else, if the left and right, or in the case where left and right are P and Q, or they are found in the left subtree and right subtree, then the current root would be the solutions. Otherwise, if the left is one of P and Q, or the right, then we return one of them. Otherwise, at the end, we return 1 to force it. Okay, so let's look at the first example. Just test the code and make sure we got the expected output. So 6. This. Let me just draw the 3 real quick. Okay. So here we go left, 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 left. And then none. This would be none, 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 none. Then this would be 2, 8. Then the answer is 6. Second example, we have, draw the 3 again. This would be none, 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 4, 2. So it returns 2 to the top. Okay. Third questions, we have 2 and 1. So 2 would be part of the solutions. We return 2. Alright, I think this should work. So let me try to put it into LeetCode. Hopefully we got it right. Is not root, return none. Left equals lowest that was common ancestor of root dot left eq. Right is the right subtree. Then check. Okay, don't remember to check whether they are valid, or actually it is handled out there. So we don't need to do this. Do I need to do the curve? Okay, let me just do it in a separate if. If current, okay, let me do it this way, root dot L equals P dot L, or root dot L equals Q dot L, return root. Okay, now if left and right, return root. Otherwise, if left, return left. If right, return right. If it is no matching at all, then we return none. Okay, so let me try to run it. Yep, we got it right. So let me try to submit it. Hopefully this will give us the correct answer. Yep, although albeit it is quite slow. But why is it slow? because we only explore the 3 ones. Interesting. I'll try to submit it again to see if it's really slow. Yep, it is slow, our solution. But why is it the case? Left and right. Can we recursively call the P and Q? If root match turn root. Can I do this equal? I think it would be the same. But the class does not implement equality. Then just curious here. Let me try to run this. Okay, it's faster but still slow. So why is that? I guess we don't need to calculate the left and right, so we could do a slight optimization here. Yeah. So if left and right return root, yeah. Finally, my implementation is considered slow here. I'm not quite sure why. Okay, let's try to look at other submissions by other people. Alright, so I forgot that it is a binary search tree. Gosh. Okay. Yeah, so it's a binary search tree. That is the important point that I missed over there. Okay. Alright, so let's spend some more time to think this through. So if we are given the binary search tree, how are we going to solve this? Now we know that given a node, previous solution, let me just write it down here, ignores that it is a BST. Now if we know that it is a BST, so let's write down the findings. One, it's possible that PQ. So if we see that p root q, then we return root. Or I think we can set the equality. So if p is less than or equal to root is less than or equal to q, then we return root. Otherwise, we need to go to one of the three. So pq is less than root, then we traverse further, meaning that we could recurse it. So what is a function called LCA? LCA of root dot left. Okay. The third cases, if we have P and Q both larger than the LCA on the right side. Now this is much more straightforward. So we define LCA root PQ. Then we check if P root Q return root, and with P root and Q less than root, return LCA of root dot left PQ, and if root is less than P and root is less than Q. Okay, don't forget there are another case where Q less than root and root less than or equal to P, which is the same, right? And then here we will return LCA of the right tree. Okay, let me check the code again to make sure I don't miss anything. If we have LCA, root P and Q, we can check whether the P and Q exists in the left and right, or either one of the child and also the root node itself. Then the root node is the answer. Otherwise, if both are left, then the answer lies in the left subtree. Otherwise, P and Q are larger than the root, meaning that our solution lies on the right hand side. So now let's go through the examples that we have. First one is 2 and 8. So we see that 2 is between 2, the current root is surrounded. It's surrounded on both sides by the P and Q. Second examples, we have both of them on the left hand side. So now we explore the left one, and we see that 2 is less than 2 is less than or equals to 2, and therefore so we return 2. Third example, 2, 1, and we see that the current node is in between the value that we are looking for. So I think that would be a solution. Let me try to input it to make sure we got it right. EP that file less than or equals to root dot file less than or equal to 2 dot file, or Q, and then we have P here, return root early P is less than 4. Return it right. Else, then they are both on the right hand side. You don't need to check the value there. This one is left, this one is right. So let me try to run it. Hopefully we got it right. Yep. And let's try to submit it. And now we got a better performance this time. Yep. So I'm just wondering if I could. I'm not sure if it is implemented. But let me try that. Oh no, it's not. So how many checks are there in here? So 1, 2, 3, 4. So there are 4 checks that happens in here. Okay. I think that's the answer, everyone. I think I'm gonna stop here, but let me just quickly go check other people's solutions. Yep, I think it's more or less the same. Let me just pick one over here. Yep, I think more or less the same as what we did over here, except that some people are using iterative approach, which may be much more efficient. But honestly, I like to do it in a recursive manner because it's cleaner to me. So I think I'm going to stop here, everyone. Thank you.